In the following task, we have the function set of t describing this arc from r to minus r along this half circle. So we have seen earlier that a circle can be described by the exponential function of it multiplied with some capital R, which is the radius of the circle. So to just have a half circle, we only need to go from t equal to 0 to pi. So here is our A and here is our B. In this example or task, we have that f of set is equal to set divided to set to the power of 4 plus 1. And we are going to show that the integral over this path denoted CR is converging to 0 as R converges to infinity. It's not very easy to do this, but we are going to see several examples of this afterwards, so you get used to it. Don't worry. Okay, what we are doing is that we are first considering the denominator. The absolute value of the denominator is using the reversed triangle inequality. We have the following. Remember that it's stated that the absolute value of the sum or difference of two complex numbers, when you're taking this absolute value, we get a number which is larger than the absolute value of the first of these minus the absolute value of the second of this. This is referred to as the reversed triangle inequality. Using this, we have that assuming that we are on this curve C of CR, we then replace set by set of t, and set of t, the absolute value of set of t is equal to r, because the absolute value is just the radius, and when we're taking the power of 4 of this, we obtain that this is equal to the absolute value of r in the power of 4 minus 1, the absolute value of this, and for large enough r, if r is larger than 1, this is the same as r to the power of 4 minus 1. Okay, now we know that the absolute value of f of set of t along this curve, which is equal to this expression, is less than, it's always less than, it's equal to r on this curve, this absolute value, but it's necessarily less than this value, because we know that the denominator is larger, in the absolute value of the denominator is larger than r to the power of 4 minus 1, then taking this fraction, we must get the opposite, namely that this is larger than this. Calling this upper bound m, we obtain the following, that using the result we showed earlier, that the integral over any type of contour CR is always less than m, which is the upper bound, multiplied with the length of the curve. And we now have both the upper bound, or some upper bound, and the length, because the length is just pi r. For a circle it's 2 pi r, but we have just a half circle, so it's pi r multiplied with this m. So then we obtain that this absolute value is less than r squared pi over r to the power of 4 minus 1. And by dividing with r squared in both the numerator and denominator, we obtain this result. And for large, when r is very large and converging to infinity, we see that this goes to 0 and this goes to infinity. So pi over this must go to 0 as r goes to infinity. So this proves what we were asked to do, namely that the integral over f of z over the curve CR goes to 0. Actually, we proved that the absolute value of this goes to 0, but when the absolute value goes to 0, then the complex number which is the integral must also convert to 0.